Well, hello and welcome to the woods. Some people sent in some questions and had some things they want answered, and maybe I have some answers, and I don't know. We'll see if we can help you out. So the musical intervals and the math involved there was asked. So I have an acoustic bass here, and we're going to maybe work in, say, work in C. Okay, well, actually, that's probably a bad idea. I'm going to work in A. If I can. All right, so there's a major scale and all that sort of stuff. And the important notes in a major scale that resonate nicely are the fifth note of the scale and the third note of the scale. So like this one right here, that note right there, and the fifth note, which is that one. So that's going to be these two, and that one, and then this one. They all should sound kind of nice together. You know, and this is the bass, so it's not simple, but I figured it'd be a low thing and you'd be able to see some stuff. So what's happening here with the ratios is, and Pythagoras figured this stuff out, is the whole length of the string, all this distance right here. If you divide that by 3, you'll wind up somewhere around here, right? But what's left over when you fret right there is 2/3 of the string. See, what happens is when the string resonates, there's all these overtones also wobbling around inside that wave. And you can find where they are by looking at the harmonics, which are here. All of those notes, you can hear that. Well, that was A. Sort of what that was. So the fifth note happens to be a ratio of 2/3 of the whole thing. Now, the whole major scale, it turns out that in order to do the second note, you make the string 8/9 as long as it had been. You cut off 1/9 of it, you left the other 8. Okay. What's quite interesting, and I learned this from you guys, which is neat, is that this note here, this third note of the scale, happens to be the square of that 8/9 fraction, which is 64/81. Now, if you do that, 64/81, you get some 0.79 number. I always thought the ratio was actually 4/5, and the third was 4/5 of the string, and that the fifth was 2/3 of the string. As it turns out, the third is 64/81 of the string, and the fifth is 2/3. I was right on the 2/3, wrong on the other one. That's why it's fun to have students working on stuff. Now, you guys are studying for finals week, and you're like, man, I gotta be done with this. So if we go to C, we can play a song by the Animals, and this is called "We Gotta Get Out of This Place." Except it takes a long time, and all I wanted to do was get down to this. We gotta get out of this place. If it's the last thing we ever do, we gotta get out of this place. Girl, there's a better life for me and you. I always go to a G there when it's an F. It's so embarrassing. Well, you didn't come here to watch me play. You wanted to talk about math, right? And so one of the other questions was about the birthday paradox and the hopeless quiz. Well, those have something in common. And the something in common is you can be wrong most of the time, man. You can be like me and be wrong like 88% of the time. But every once in a while, accidentally, you're going to be right. You know, like that broken clock is right like once a day if it's got 24 hours on it, twice a day if it's got 12, right? And the hopeless quiz, well, you know, whatever that was if you had 20 questions and you had no idea what any of them were, and so you just did that advice of, oh, answer every question because then you get some points. You got a 75% chance of being wrong the first time and 70% chance of getting wrong, 75% chance of being wrong the second time. Let's just deal with those two, all right? If you answer 2 questions, you have possibilities. Maybe you got them both right. Well, the odds of that are pretty slim. The odds of that are only 6.25%. You probably got it wrong. You probably got the other one wrong too. But what if you got them both? The odds of being right both times is really slim. It's just 2 questions. But the odds of being wrong both times are not all that high. It's a 3/4 chance of a 3/4 chance, because you got this idea of, well, I could have been right, but no, I was wrong. And then I could have been right, but oh, I was wrong. So you got to get on the wrong channel twice. 3/4 times 3/4 is 9/16. And 9/16 ain't all that terrible a thing. You keep going again and again and again. And the idea is, well, I didn't know anything. I probably got a 0. No, you probably didn't get a 0. You probably accidentally got something right. You just don't know which one. And so that's what that is. Birthday paradox is the same idea. It's like, hey, you got my birthday? No, probably not. Okay? The odds of not having my birthday are 364 out of 365. Forget leap days. So if you have a bunch of people around, it's like, hey, you got my birthday? How about you? How about you? And then they're like, I don't have yours, but maybe you have mine. Maybe you have mine. And the question is, how many pairs can you get to keep playing this game of, hey, you got my birthday, over and over and over again? And the number of pairs you can have, this is kind of an interesting fact, and it relates to the Gauss problem of adding up all the numbers from 1 to 100. Is if you add 1 plus, 1 is 1. 1 plus 2 is 3. 1 plus 2 plus 3 is 6. 1 plus 2 plus 3 plus 4 is 10. So 1, 3, 6, 10, dot, dot, dot. Those are the triangular numbers. Now dig. You got 2 people in a room, you got 1 pair. You got 3 people in a room, you can say, yo, you leave. Then you got a pair. Or you can say, no, you leave, and you got a pair. You can say, I'll leave. And the other 2 are a pair. So with two people in a room, 1 pair. 3 people in a room, possible to build 3 pairs. 4 people in a room. First person can be paired with 3. And then you say, okay, we tried that. Second person can be paired with either of the other 2, and the last person can be paired, well, the last 2 are just there, So that winds up being, this was 4 people, that winds up being 6 possible pairs, 3 plus 2 plus 1. Look at these answers. They're the triangular numbers. So the question we want to ask is, to what triangular number do we raise the fraction 364 over 365 before the answer is less than 0.5? The answer is 253. And then you say, well, 253 people? No, 253 pairs. And that means the 253rd triangular number. 253 is kind of a fun number because it's 230 plus 23. That's right. It's 23 times 11, right? Now, why is it 23 times 11? Because it is. Do the Gauss problem. You got 23 people. You got, let's say 22 people. You got the first person and the last one, and those add up to 23. And then if you have 22 people, you have 11 pairs like that. So you do 11 times 23, and you get 253. So once you get past that, that gives you 0.5 something. Once you get past that, you're beyond the 0.5. That number actually gets, if you do 364 over 365 to the 253rd power, you should get like 0.5001 or something like that. So as soon as you go beyond that, then you wind up at there's likely a match. And that's what happened for us. There's likely a match. So we got the intervals, got the hopeless quiz, we've got the birthday problem, we got the Gauss problem. What else came in? Someone wanted to know about the freshman dream. And we have Garfield's proof of the Pythagorean theorem, the infinity of primes. Let's stay on number theory and do the infinity of primes. It just goes like this, dudes. What's a prime number? It's a number that you can't divide other stuff into, So if you do try to divide other stuff into it, you get a remainder. Well, the easiest remainder is 1. So let's just do a quick example here and take the number, I don't know, it's composite like 45. 45 is 5 times 9, right? Now, neither of these is prime, but it's 3 times 3 times 5, but so what? If you take 45 and add 1 to it, okay? If you put 5 into 46, you're going to get 9 remainder 1. You get a remainder of 1. If you put 9 into 46, you're going to get 5 remainder 1. And that happens all the time. Take the product of 2 numbers, add 1 to it, divide those numbers in there, and you'll get remainder 1. Well, that also works. You take the product of 3 numbers, or 4 numbers, or 5 numbers, or 6 numbers. Take any number that is a multiple of some number, add 1 to it, divide that factor into that new number, and you're going to get remainder 1 every time. So let's answer the question about how many prime numbers are there by saying, I don't know, but suppose it is a finite number. It's a big, long list. You get 2 and 3 and 5 and 7 and 11 and 13. It goes on and on and on and on. Let's pretend you're really, really, really good at arithmetic. And you know all those numbers, and you multiply them all together, and you get some huge prime number. Oh, wrong, sorry. Some huge composite number. And then you add 1 to it. And then you say, oh, let's test this out. You divide every known prime into it and find out, is it prime? And in every single case, it's going to be like, no, remainder 1, no, remainder 1, no, that doesn't go in there. And every single time, you're going to get a remainder. So every single time, you find no factor. And so at the end, you say, well, then this one must be prime too. And see what just happened? Your whole world exploded because you said, these are all the prime numbers. And a logical conclusion of that is, except for this one that I left out. And if you left one out, then you didn't have them all. So the idea that I have all the prime numbers must have been false. And therefore, the concept that you could have all of them is false. And therefore, you can't have all of them. And therefore, there's infinitely many of them. That is called the proof by contradiction. Right. That's infinity of primes. Hope that was fun for you. Garfield's proof of the Pythagorean theorem. You know what I'm going to do for that one is say, look it up. I'll explain it just as fast as I do. It looks like Pythagoras' picture cut in half. So try to remember Pythagoras' picture, tilted square inside with the 4 triangles around. Just cut that middle square in half and look at that. See one triangle, another triangle, slanted square. As far as the algebra and all of that, that's going to be on the next, what we're about to talk to you about right now. So I'm not going to really go into depth on it, but if you really want to know about how Garfield proved the Pythagorean theorem, type in Garfield's proof of the Pythagorean theorem. Boom. It'll probably be explained by the YouTube, but it's easy. You'll have fun with it. So that's that. But special products. So people asked about the freshman dream. Freshman dream is a mistake, and you don't want to make that mistake. It's the same thing as the mistake of saying, 5 times 5, I know that. That's 13. Yeah, that's not true now, is it? But 5 is 2 plus 3, right? And so I can take 5 plus 5 and make it into 2 plus 3 times 2 plus 3. And that's 2 plus 3, the quantity squared. So I put my parentheses, I put a 2, I put a 3, I put a little 2 up here. It's exciting. I get 2 plus 3, the quantity squared. And now because I'm smart, I will distribute my exponent onto the 3 and the 2. And 2 plus 3, the quantity squared, is 2 squared plus 3 squared, because the square of a sum is the sum of the squares. And 2 squared is 4, and 3 squared is 9, and 4 plus 9 is 13. And that's what 25 equals. Yeah, something went wrong there. And what went wrong there was trying to distribute an exponent onto some addends. See, addition is not next to exponentiation. Addition, multiplication, exponentiation. So I can distribute an exponent on a times b and say a times ab, the quantity squared, is a squared b squared. Cool. And I can distribute a coefficient onto a plus b and say m times a plus b is ma plus mb. That's cool. But I can't distribute an exponent onto some addends. That's crazy. That's like trying to go up, first step on the first flight of stairs and the next step on the third flight of stairs, and somehow you're going to get upstairs that way. Only with really long legs will you make it that way. But you'll be leaning the whole time. It'll be awkward. So special products are not the sum of the squares. But the difference of two squares, that is a special product, and that was a lightning calculator trick. Let's take, for example, if we're doing, 27 times 33, okay? And we look at them and say, ooh, they're both 3 away from 30. So the answer is going to be 9 away from 900. So I guarantee you put in 27 times 33 into a machine, or you just work it out with a pencil, which is another machine, and you're going to find the answer is 891. So that's fun. That is based on the idea that a squared minus b squared is what you get when you have a plus b times a minus b. And you FOIL that guy, the a squareds happen, the b squareds happen with the minus sign, but the plus ab and the minus ab, they cancel out. And you wind up with a squared minus b squared is a plus b times a minus b. So that's all I did for 27 times 33 was, 30 squared minus 3 squared. So 900 minus 9. Lightning calculator. Now there's a 5 trick too. That involves doing some FOIL, and you can hunt around that one if you want to. If this isn't your thing, it's not your thing. So you don't really have to. There'll be some other question there, hopefully, if you have that. But I do want to mention that the square of a sum is a squared plus 2a. A plus b, the quantity squared, is a squared plus 2ab plus b squared. And that middle term is important. If we go back to the freshman dream problem here, we had 2 and 3. If we wanted to get that right, we got 13 before. But if we did 2ab, which is 2 times 2 times 3, that would be 12. And if you add that 12 to that 13, boom, we're right now. 5 times 5 is actually 25. So that's fun. Gauss film, we talked about infinity of primes. We talked about the, linear systems. Yes, a few people said, what about linear systems? Well, learning how to work with linear systems is an IM1 lesson, an IM2 lesson. I'm going to let somebody like Sal Khan tackle that if you're wondering what to do there. But there's a technique when you have two equations that are in standard form. We have their coefficients. And that sometimes is called elimination. Sometimes it's called linear combination. A lot of the other stuff they call substitution. But if you're doing elimination or linear combination, what you want to do is match the coefficients on one unknown. And then what you want to do is either add, if they match, have the same magnitude but different signs, you add them up to get rid of them. Or you subtract. If they're the same magnitude and the same sign, you just do a subtraction problem. And then that's gone. And then you're left with one unknown times something equals some number, and you just divide and then you get your answer. Right? Where we use that, we did it twice. We did it in if you have 3 points that are on a circle. And the idea here is that you know that 3 points that are on a circle are going to also define a triangle. And that triangle is going to have a circumcenter, which is the center of the circle. It's going to hit all 3 vertices. So that definition of center of a triangle is kind of useful. So what we did is took the general equation of the circle, which is this: x minus h, the quantity squared, plus y minus k, the quantity squared, equals r squared. If you look at that, x minus h, the quantity squared, plus y minus k, the quantity squared, equals r squared. The thing squared plus a thing squared equals a thing squared. It's just the Pythagorean theorem. But it's been translated around and turned into a circle and all that. So if you have 3 points, what we're trying to solve for to get the equation of the circle is, what is the h? What's the x coordinate of the vertex of the center? What is the k? What's the y coordinate of the center? And what is the radius? What is the r? So what you can do is you can plug these points in to the circle formula, and you'll get something where you FOIL stuff and you get a whole bunch of big long equation. And it's got like h squared plus something. Like if I had to point like 3, 1, right? That would give me, because what I'd be doing is 3 minus h, quantity squared. What I would get is h squared minus 6h plus 9. And if the 1 was the other point, it'll be plus k squared minus 2k plus 1 equals, and then r squared, whatever that is. And the r we're not going to worry about this, because when you do this 3 times, you have 3 things to choose from. You can grab any 2 of those 3 and say, I'm going to subtract this one from this one. And you will subtract every time. Because what will happen is the coefficients match. The coefficient on h squared is 1, and same with k squared, and same with r squared. When you subtract them, h squared minus h squared, gone. K squared minus k squared, gone again. Y squared minus, well, y, r squared minus r squared, gone a 3rd time. So all of the 2nd order terms, the square terms, vanish, and you're just left with 1st order terms, and you get yourself down to a linear system. So you take the circle equation, set that out 3 times, and then get a linear system. We did the same thing for, what I mean by linear system is 2 linear equations, and in this case, 2 linear equations in standard form, which means that the x and y, or the h and k, or whatever you're looking for, are together on one side. In the case of the quadratics, it's going to be an a and a b. And the reason why is this. We also did it for quadratics. 3 points will determine a unique parabola. So you plug those in and you get some stuff. Plug those into ax squared plus bx plus c equals y. So the y is just sitting over there by itself. That's simple. The x term is going to be ax squared. You square the x, and you get like, so if x is 3, then you get 9a, okay? Plus 3b plus c equals whatever the y value was. When you do that 3 times, you're going to get these perfect squares and the thing themselves. And the thing that's going to disappear first is going to be c, because the coefficient on c is 1. So you subtract 2 equations, the c is gone. And then you wind up with these, a linear system in standard form, and use the exact same technique. So if the question was, how do I work with a linear system? Go ahead and look around for that sort of stuff. But if the question was, how do I use a linear system? The idea is plug the values that you're given in, and then strategically get rid of something. If you're doing a circle, subtract to get rid of h squared, k squared, and r squared first. Take 2 equations and get rid of those. If you're working with the parabola, subtract to get rid of c. And then what will usually happen is you'll find your coefficients work in such a way that the next thing you get rid of is b, and you wind up solving for a, then use that to find b, and then use that to find c. So there's that work, and I hope that's helpful to you. And I think we are done with all of the requests. So I guess I should say goodbye to you. We gotta get out of this place. If it's the last thing we ever do, we gotta get out of this place. Girl, there's a better life for me and you. I know it's true. You do too, maybe there. Something, right. If they do it one more time, then they go, and it ends. Yeah. So it's a good song. We gotta get out of the place from the animals. Hope you enjoy it. That's why I played live by 11 Rockets at the Aragon Ballroom when I was 10 years old. I wasn't 10 years old, I was 22. Bye-bye.